using graphs. So it's not just using graphs in math per se. In fact, the example that they give you in your books that you would have read about here is with this largemouth bass. And they have basically given us a chart of the age of the fish versus how long the fish is in inches. And so what you'll notice is this chart should look very much like the relations and the functions that we have been talking about. You have this comparison of the years to the length, okay? And so this is like your X and your Y. It's a comparison of two things. And so that's actually what they've done. They have plotted it on a graph. And so they've created this graph. They've labeled this bottom part here the age, and this what would be the Y, the length. You'll notice that there is no negative because obviously we can't have negative years for the bass and we cannot have negative length for the fish. And then they've just plotted these points. Now, when you have anything that grows, it's not going to jump in growth. So it's not like it's going to go from 6.5 inches and just boom, all of a sudden be 11 inches, right? It's actually going to gradually grow. And so what they do to represent that is they connect those dots with this curve. Because this is a gradual process. When you go to the doctor year after year and they measure how much you've grown, they don't expect that you went to sleep one night and the next night woke up 4 inches taller. That's not how it works, okay? And so this arch here that they have represents that gradual change in length, all right? And so then from this, you can kind of make an assessment as to what will happen. Now, I will say growth plateaus out, right? So as you can see, just like the fish, just like with people, you don't continue to grow your whole entire life. It's not like when you see an old person that they're 18 feet tall because they just kept growing, right? We plateau out. About in our 20s, we just stop growing. And so that also happens with the fish. So you'll notice that it does plateau here. But if I were to say, well, what about at about 3.5 years? How long do you think the average fish would be here? Well, you could plot that and you could say, well, it would be about 15 inches based on the information that they have. All right, so once you do this curve, you can then pick points within the curve and you can make an assumption based on what your assessment is of what you have gathered in the data. And so they'll do this a lot in science as well. You'll see these examples. All right, if you look at the next one, the next example is with postage. And so they said, model the first class postage rate given the table and state the general characteristics of the rate of increase over the postage. Predict what will happen in 2050. And you'll see that they took this and they put this postage here. Now, you'll notice that it stayed the same for quite some time. If you were to draw this here, it stayed the same. But then probably around here in the 1960s, postage started going up. And then there was this steady increase where they just do, usually it's just a few cents a year actually that they do postage. And not even every year that they change the postage rate. And so then from there, they drew a line. All right. And so you'll notice that at first, postage didn't really seem to change for a long, long time. And then we started going up. And it's pretty steady. I mean, it does kind of bounce a little bit. So it's not like you could draw a line that is perfect here. But you can draw just this line here that kind of gives a picture of what's happening to the postage. It's not exactly on every single dot, but it's kind of an average in between them to show that increase. And so if we were to assume what would happen then if it kept doing what it is doing right now, then what would it be in 2050? Well, we're just going to take the 2050 and we're going to go up. And then once we go up with the 2050, we are going to go over. And so we're going to say, well, at 2050, it crosses right there. So if we go over, we can say, well, our prediction is it'll be about 80 cents for a postage stamp by the year 2050, if it keeps increasing. Now, this is based on the information we have, and information could change, right? And so in 2050, we may not even be using postage, right? Because very few people actually use it now. But that's what we're looking at when we just look at the information that we have. So for this example, it says use the distance time graph to answer the following questions. Now, I will say this graph looks like when I look at it, it looks backwards to me because this is a skydiver that is falling. And so the picture of the graph that I would get in my head is what? Not that it's going up, but that it's going down. But what they're asking for is distance, okay? How far he has fallen. So distance is actually always positive, right? Direction is negative. So if he's falling, obviously he is going down as a skydiver. But now we're talking about distance. So how far has he traveled? And so that's why it's going up. If you were to flip it upside down, you'd actually see what it actually looks like when he falls, right? But you'll notice that, let's say he did skydiving right from the airplane. At 0 seconds, he was still in the airplane, right? So he had not fallen any distance whatsoever. After 10 seconds, you can see that he had fallen, probably at about 11 seconds here, 1,500 feet, okay? And so you can see that based on the time and the distance, we can answer these questions. How far has the skydiver fallen after 10 seconds? Well, if I go to 10 seconds and over here, I would probably say around 1,400, somewhere around there, 13 to 1,400, all right? This is an estimate, all right? So at 10 seconds, maybe 13 to 1,400 feet here, okay? And then it says, how long did it take? Well, now they're asking for seconds. How long did it take for him to fall 2,000? Well, now we're going to start on this axis. 2,000, how long did it take? Well, it's in between the 10 and the 15. So here, again, maybe about 14 seconds. How long did it take for him to fall 2,000? Probably about 14 seconds, all right? And then describe the fall of the skydiver in the first 5, the next 15 seconds, and the final 10 seconds. So 5 seconds, you can see it's a little bit curved here. He fell 500 feet. Then you can see he fell pretty rapidly for the next 15 seconds. So 5 to 20 was pretty rapid, okay? What would have changed here that would slow his descent? It's pretty important for a skydiver. A parachute, okay? And so when you're interpreting this, you can see when he first takes off, he's gonna have a little bit of resistance jumping out of the airplane, but then it just shoots down. Basically, he's gonna fall very quickly. At this point, we're hoping a parachute probably opened and it slowed his descent, all right? And then eventually you're gonna see this plateau and stop. Why would it stop? He's on the ground, all right? And so when you're looking at graphs, you are interpreting what is happening based on the information that you have, all right? So let's look at the last example here, top of page 203. This actually doesn't have any numbers at all on the graph, right? So there's no numbers at all on the graph. The Wadsworth spent a day hiking in the mountains. Mrs. Wadsworth GPS-enabled sports watch records her heart rate and her position, including altitude. Analyze the following graphs produced from their trip to describe their hike during each period. So this top graph is a graph of her heart rate, and this is based on time. And actually, they didn't even put numbers with the time. These are segments of time where it checked her heart rate. And then the bottom graph is altitude compared to time. Now, if we look at the altitude graph, what do you notice from like A to B? What's happening? They're going up. So if they're hiking here, we're assuming they're climbing, right? Notice her heart rate. It started here and it jumped pretty significantly from A to B. Why would that be? Well, she's climbing, all right? You can see that from in this B block, right, that her heart rate dropped and pretty much leveled out. Well, what do you notice in this block? They're no longer climbing. And then in the C block, they actually go down. Why would, I mean, if you've ever hiked, your heart rate does go down when you're going, does go up when you're going down. Why?
Because it's like a lot.
You're having to stop yourself, right? It's not going to go up quite as much as if you're climbing, but you are having to use a little bit more momentum than just walking on a plateau, okay? All right, we start altitude again. We notice heart rate again. We level off, heart rate levels off. Going down, heart rate goes up some. All right, and so you can see how those two graphs actually go together, even though visually they don't look anything alike, okay? Visually they don't look anything alike, but you can see how the two would go together based on heart rate compared to altitude, okay? Even though they're two separate graphs. Make sense? All right, so let's talk about these two. Interpret the first graph. You'll notice at 12 a.m. we don't have a lot of cars. What do you think happens here? What would be your assumption here? Everybody's going to work. So this is probably when rush hour starts and the peak of rush hour here. You'll notice that it goes down a little bit, back up. What is another time of day that it might be kind of busy? Lunchtime. It peaks all the way to the highest point. This is probably when people are going home, right? And it gradually tapers off, right? So, yeah, that's what you're going to interpret from intersection, right? The intersection would be busier certain times of day. Ken's distance from home as he travels to the grocery store. What is his distance going to start at? 0. He's at home, right? And then he is going to travel to the grocery store. So however far away the grocery store is, that's how far he's going to go. What's going to happen in the 30 minutes that he's at the grocery store? It is going to stay the same. So we're going to plateau here for 30 minutes. And then what should we see that graph do, assuming he goes back home? It should go back down all the way to 0, actually, all the way back home. Easy enough? All right.